Okay, so chapter 6 is the beginning of the thermochemistry stuff, and a lot of this should be reviewed, so I'll go pretty quickly. Energy is the capacity to do work or produce heat, and we say that energy comes in two forms, either potential energy or kinetic energy. Okay, potential energy for chemistry usually means that you have energy stored in bonds, and kinetic energy refers to the movement of particles. Okay, the law of conservation of energy states that energy can never be created or destroyed. It can only be converted from one thing to the next. So we're going to be looking at that energy transfer for different chemical reactions. Okay, heat is the transfer of energy, okay, due to a temperature difference. Temperature is a measure of how quickly your particles are moving. So if your particles are moving really quickly, they have high kinetic energy and they have a high temperature. Okay. We will talk about energy or heat as being either on the products or reactants side of reaction. So we've talked about already how when energy is a product, this is an exothermic reaction. Okay, when it's a reactant, that would be an endothermic reaction. Okay. So usually we talk about thermochemistry in terms of the system and the surroundings. Typically the system is the reaction, or whatever you're focused on, and the surroundings is everything else. So what's outside of the system, and together they make up the universe. Okay, so in exothermic process, we have energy or heat as a product, and endothermic, it's a reactant. So exothermic means that heat is leaving the system or the reaction. Endothermic means heat is going into the system or the reaction. Okay, so again, represented pictorially, something is leaving the system, it's going to the surroundings, and so it's exothermic. Okay, into the system is endothermic, because we're always looking at it from the point of view of the system. Okay, and of course that energy or heat has to be coming from the surroundings because of the law of conservation of energy. Okay, so enthalpy is basically heat, and we'll be talking about enthalpy, which is represented by the symbol H. Okay, we'll usually be talking about the delta H for a reaction. So in other words, how the heat of reaction is changing over time. Okay, so delta is always final minus initial. So for us, if we're looking at the delta H of a reaction, that would be the enthalpy of the products minus the enthalpy of the reactants. Okay, and by seeing how they change over time, that's going to tell us whether the reaction is endothermic or exothermic. So if our delta H is negative, that means we have an exothermic reaction. So you should remember this from Le Chatelier's principle stuff. That means that heat is leaving the system, so it's a product. Okay, that also must mean that the enthalpy of the products is less than that of the reactants. Okay, as you can see in this graph here, because if you're subtracting them, that would give you a negative value. Okay, and of course the opposite is true for an endothermic reaction. So if you have heat as a reactant, your enthalpy of your products must be higher than that of your reactants. Your system's enthalpy is increasing, see the positive delta H value. Okay, and again, this is just represented pictorially the same thing. Okay, a calorimeter is a way of indirectly measuring the enthalpy of a reaction. Okay, so you can imagine this is a calorimeter. You can use just like a tin can for a calorimeter. And this is like it cut open so we can sort of see the inside. And there is a thermometer in the water here. This water is the surroundings. Okay, so that's what the thermometer is measuring the temperature of. And then you notice there's this reaction on the side, and this will be your system. So depending on what is happening to the temperature of the surroundings, you can tell indirectly what's happening to the system. So the that means that it's endo for the surroundings. Okay, therefore the opposite for the system. So this reaction, exothermic what we're measuring or focusing on. And so, of course, the opposite would be true if your temperature was decreasing. It would have to be endothermic for the system. Okay, so you're indirectly measuring the temperature of the system by measuring the temperature of the surroundings. Okay, and we have this equation that we use for talking about heat transfer, which is Q equals mc delta T. Q is heat or energy. M is mass. Delta T is the change in temperature, and you can use either degrees Celsius or Kelvin for this, because when you subtract two things, their difference is going to be the same no matter what, but you'll see degrees Celsius a little bit more. Okay, C is derived from the other variable. So if you isolate C, you get C equals Q divided by M delta T. So Q is joules, M is grams, and then delta T is degrees Celsius. And so these are your units typically for specific heat. Okay, so we're going to look at an example to tell us what specific heat actually is. So if you have 1 gram of iron that's heated from 50 to 100 degrees Celsius, and that requires 25 joules of energy, while 1 gram of silver that has the same temperature change requires only 11.25 joules of energy, those two metals have different specific heats. Okay, so having a different energy required to change the same mass by the same temperature, those two substances must have different specific heats. The amount of energy required to raise the temperature of 1 gram of substance by 1 degree Celsius. So again, what specific heat is indicated by the unit. So the amount of energy required to raise 1 gram by 1 degree Celsius or Kelvin. Okay, so the lower your specific heat, the easier it is to change the temperature, or the less energy must be applied to change the temperature. So question 1, which substance heats the least if 1 gram of each of the substances above is heated by the same amount of energy? And if you think about it, you should realize that the lower specific heats should heat more easily, which means that here, the one that heats the least is the one that has the highest specific heat, so that would be water. Okay, and then for question 2, the one that heats the most would be mercury, because it has the lowest specific heat. Okay, the next set of problems you should be able to solve fairly easily, so go ahead and pause the screencast to solve those problems, and I'll go over the answers to those. Okay, so A should be 0.45 joules divided by grams times Kelvin. Letter B should be 54 joules. Okay, and C, you need to do a little bit of stoichiometry. So all this is you're converting moles. So you're given a specific heat, incorporate by okay, and since you're dealing with iron, all you have to do is say 1 mole of iron has a mass of moles. So then that becomes 25 joules divided by grams times Kelvin. Okay, and then for the second set, A should be 900 joules, B should be 26 joules divided by degrees Celsius times moles, and C should be 1,630 grams of silver. Okay, this next equation, negative mc delta T equals mc delta T, is obviously just a derivation of the one that we were just using. So this is an indication of energy always being transferred. So this is the same equals positive. Which one is which? Because all you're saying here is that the energy transferred from one has to be coming from the other and vice versa. Okay, so they should be equal but opposite to one another. Okay, so let's look at a particular example. You have 15 grams of aluminum. You're given the specific heat for that, and it's heated to 400 for aluminum. Then that aluminum is dropped into 125 grams of water that has its own temperature initial. Okay, then they're combined, and the question is, what is the final temperature? So the temperature final is always going to be the same for both. So you actually only have one variable here, because we know that when we combine two things that have different temperatures, eventually their temperature will be the same thing. Okay, so you have to isolate TF, and you have to do a little bit of distribution, and you end up finding that the temperature final for both of them is 304.3 Kelvin. Okay, and that should make sense based on the initial temperatures. Okay, and then you can pause so you can solve the second one, and you should get your answer to be 25 grams. Okay. Okay, so let's look very briefly at how stoichiometry relates to this chapter. So you have a particular reaction balanced for you, and the question is, how much heat is evolved when 54 grams of burned? So again, you have some laid out here for you. So this is one whole glucose. Okay, you have negative 2,808 kilojoules that are evolved. So all you have to do here is basically, okay, so one has a mass of 180 cancel, and then 208 kilojoules. Okay, and then when you multiply those together, you get negative 842 kilojoules. Okay, so you should be able to solve the bottom one on your own, and you should end up getting negative 8,535 kilojoules. Okay, so the final section that we'll go through, I'll have to bridge into another screencast, but this is Hess's law. So Hess's law is a result of the fact that enthalpy is what's called a state function. It means that the pathway that we use to arrive at the answer doesn't matter. So the enthalpy for a given process is always going to be the same as long as the reactants and products are the same. We don't care about the steps required to get to those products from the reactants. Okay, so Hess's law says that in going from a particular set of reactants to a particular set of products, the change in enthalpy is the same whether the reaction takes place in one step or in a series of steps. Okay, so let's look at this first example. Okay, so you have a reaction and you're given the enthalpy value for it. Okay, let's pretend for a second that we didn't know what this was. Okay, and you just have the information below. So you have two different reactions and you are given their enthalpy values. Okay, when I add these two reactions together, okay, you notice that that just means that all the reactants are going on one side, all the products are going on the other. NOs cancel, and then you're left with N2 plus 2O2 yields 2NO2. All you have to do to find the enthalpy value of this reaction when you've added them together is to add their two separate enthalpy values together. Okay, and you notice that this matches the reaction from above, and its enthalpy value is exactly the same. So by adding together those two reactions, we got the reactants and products to look identical, and therefore we could also figure out the enthalpy value. Okay, so this is just a pictorial representation of the fact that we can imagine like a few different ways, okay, of getting. So this would be like the pathway, and these are your reactants, these are your products. There are many different ways of getting to the same set of reactants and products. Okay, but as long as they match, the reactants and products match, the enthalpy value is always going to be the same. Okay, so two ways that we can manipulate equations is either by multiplying them by a number, and that can be a fraction or a whole number, or we can reverse the reaction, which means that the reactants become the products and the products become the reactants. If we reverse the reaction, then you must negate the sign of the delta H. Okay? If you multiply the reaction by a number, you must also multiply the delta H by that number. So basically, whatever you do to the reaction must also happen to the delta H value. So we'll get to why these manipulations are ways that you can manipulate reactions in order to get them to look like